Hello, this is Math 280, Multivariable Calculus. I'm Professor Wheatley. Today's topic will be curvature and the unit normal vector n. And this is going to be the second of our 3 lectures dealing with motions in 3 space. So, what we have is some particle. So as a particle moves along a space curve r of t, well, t, which was the unit tangent vector we talked about last time, changes direction. Remember, t was always pointing in the forward direction of the curve at any time little t, right? Okay? Well, the rate at which capital T turns per unit of length has a name. That's called curvature. And we'll use K to denote that. And so curvature is what its name implies. It's a measure of how twisty and turny a certain space curve is. So definition. So the curvature at time t, K of t, is equal to the length of the derivative of capital T, dt ds, as such. Therefore, K is a magnitude, or a length, of the rate of change of T with respect to, remember S was arc length S at time t. Right? And so K is a length of the rate of change of t with respect to arc length S. That looks like it says arc length, but that should really be arc length S, like that. Okay? And why use arc length? Well, remember, arc length is great because it's constant regardless of what parameterization we use for the curve. So we use arc length since arc length is constant regardless of parameterization used for the curve. Right. Okay. So what does this mean? Well, curvature, unlike arc length, curvature can be positive, negative, or 0. Arc length can be the same thing as directed distance. So what happens with various degrees of curvature? So if K is large at a point P, T turns sharply as the curve passes through P. And I've just realized I've made an error in saying something earlier. So arc length is directed distance. It's positive, negative, either way, depending on which direction you're going in. Curvature is a length, so it's a positive value only. So disregard my earlier statement. Curvature is a positive value only. If curvature is large at a point P, then T is turning sharply as the curve passes through P. And if K is small at a point P, then T is turning more slowly as the curve passes through P. Right? And remember that curvature is going to be greater than 0, unlike S. Right? Okay, so what we'd like to have, we want curvature. Right now we have it in terms of dt, d capital T, ds. We would like curvature in terms of little t, not s, right? We want curvature in terms of the time variable, not the arc length, right? Okay? So, k of t is equal to that length of dt ds right there. All right. So let's use chain rule on this. All right. So if I use chain rule, I get dt ds times dt ds as such, right? So it doesn't look right to me. Why not? Oh, wait, because this is dt dt, right? That look right to me? Yeah, that looks good. Okay, that's much better. All right, so there's chain rule. So that's chain rule. All right, and then what do I want to do now? Properties of absolute value allow me to write it as this. So this is ds dt. So notice this is multiplication in the middle. I'm going to break up the absolute value, two different absolute values here. And dt ds is the same as 1 over ds dt, right? Flip the fraction in the bottom, yeah? So this is absolute value properties. It's just algebra there. All right, absolute value properties. And last but not least, what now? Oh, yeah. So let's see here. This is 1 over, well, let me write it like this. So let's leave this here. Dt dt, like that. And this is 1 over, do I want a t in there? I do want a t in there, don't I? So 1 over v of t, like that. Remember, ds dt is the derivative of arc length, and this is the length of it. So that would be 1 over the speed. That was a result from the last section, right? So this is a result of last section that we had. Okay? All right. So now, why is this nice? Well, because now the only variable down here is t, little t, so that's good. So let's go ahead and try this formula out here on an example. Let me get rid of this. And there's a nice intuitive example we can use here to make sure this is actually working like it's supposed to. So what about a linear space curve? So think back to the section on equations of lines and planes in space. So we have r of t, let's see, 1 plus 2t I plus what? 3t j plus negative 3 minus t k. So it's a linear space curve. It's a line in space. And let's see here. So the derivative, v of t, well, these are all going to have constant derivative up here because they're all linear terms. So this is going to be what? 2i plus 3j, and that's going to be what? Minus 1k or minus k, like that. What I've got here? Good, yeah. Okay. The length of that, the length of v of t, 2 squared is 4, plus 9 is 13, plus 1 squared is 14, so we got root 14. Remember, unit tangent vector, t of t, is just the direction of v of t, right? v of t normalized by its length, yeah? So this is going to be what? 2 over root 14i plus 3 over root 14j minus 1 over root 14k is how t should look. Okay. And well, dt dt, this derivative, well, these are all constant terms. The derivatives are all 0. So your derivative is going to be the 0 vector, right? Okay, well, great. Well, we're almost done here. Let's just get ourselves very formalized. Remember, k is supposed to be, it's 1 over the length of v times the length of dt dt. Well, hey, 1/14, the length of the 0 vector is clearly 0. So this is just times 0. So curvature is 0. So why is such a nice intuitive example? Because we expect that on a linear space curve, right, on a line, capital T will always point in the same direction no matter where you are on the line, and therefore there should be no curvature, all right? So let me say that over here. So T always points in the same direction on a line, right? And so there's no curvature. So no curvature at any point. Okay? All right, so there's curvature. Now, we talked about capital T last time, unit tangent vector, and I said it was one of three vectors that will allow us to analyze particle motion in 3 space at any time little t. Well, here's the second vector in that group. So let's make some room here. So big T always pointed in the forward direction. What else is important to us? Well, what about big N, the unit normal vector? And remember, normal just meant perpendicular. Right? So this vector should be not tangent to the curve, but perpendicular to the curve at time t. Okay? Now the fact is, at any given point on a smooth space curve, I want to call it R of t, there are many vectors orthogonal to t, right? So you have some space curve, you have some point, you have your unit tangent vector t. Well, there are lots of vectors that are orthogonal to t. In other words, any vector that when you dot it with t gives you 0 will be orthogonal to it. Okay, which one do we want? Well, since t is a unit vector, then the length of t, I should say length En, is constant. And if we think back to the important result from vector-valued functions, or one of the important results we learned was that if you have a vector of constant length and you dot it with its derivative, then you will always get 0. In other words, a vector of constant length is always orthogonal to its derivative. All right? So by result from, what is it now, 3 sections ago? 3 sections ago. That's section 13.1 in Thomas, but depending on what your book is, whatever the section on vector-valued functions is, right? Then if we take t of t and we dot it with its derivative, t prime of t, then we get 0, right? And so t prime is a vector that's normal or orthogonal to t, okay? Well, again, t prime may not be a unit vector, but it's always easy to make a unit vector by just dividing by the length. But take t prime of t, divide it by its length, t prime of t, by its length, and you do get a unit vector. And in particular, this is called, so this is N, which is the principal unit normal vector at time t. There's a mouthful for you. So that's N, the principal unit normal vector at time t. So again, we have some unit tangent vector, and now we have a vector that is orthogonal to that vector and a unit vector. Okay? Okay, so here's a picture to show what's going on. Let me get rid of this. So let's look at an actual space curve and see what's happening. So there's a space curve. Here's a point, P1, right? Unit tangent vector maybe, something that looks like that. So there's T, and we'll be multimedia here. So at a right angle to it is n, right? So those two vectors are orthogonal to each other, right? Okay, and we can show it again on another point. So here's another point. There's P2. Let's see here. Unit tangent vector, looking like that. Unit normal vector. Does that look normal? More or less. Well, vector like that, right? Okay. And so at each point, T and N are orthogonal. T is the vector pointing in the forward direction of the curve, right? At any given point on the curve. And N, so what do I want to say here? So N points, so let me say this. So T points in the forward direction, point P, and N points in the direction the curve is turning at point P. Right? So T points in the forward direction, moving with the curve, pointing in the direction it's turning, pointing in the direction it's turning. Okay? Look at an example here. So there's the picture. All right, let's try to find curvature and n for a nice helical space curve. So let me get rid of this. So here's our old standby, the helical space curve. 2 cosine t I plus 2 sine t j plus tk. Okay? And I want to find curvature and unit normal vector n. Okay. All right, so velocity vector here. Remember v of t, which is r prime. Derivative, negative 2 sine t I. Let's see, derivative of sine is cosine, so that's going to be plus 2 cos t j and plus k. What else do we need here? We need the length. So the length of v of t. Let's see, so that's, this is 4, because it's cosine sine squared is 1, plus 1 is 5. This should be root 5, right? And I'll just write that out. So this is, 4 sine squared t plus 4 cos squared t plus 1. There you go. Okay, so there's v of t. Now we also need t, as in capital T. So capital T is v divided by its length. So we're talking a negative 2 over root 5 sine t I plus 2 over root 5 cosine t j plus 1 over root 5, don't we need the parentheses, do we? 1 over root 5k. All right, looks good. We also need t prime, so there's t. We need t prime. So t prime, let's see, so the derivative here, derivative of negative sine is negative cosine, so that's negative 2/5 cosine ti. Derivative of cosine is negative sine, so we're talking negative plus negative 2 root 5 sine t j. And this zeroes out because it's a constant, so we're done with that. Everything looks good there, yeah. We need the length of t prime, so a lot of stuff we need here. So a length of t prime, which is what? It's 4/5 cosine squared t plus 4/5 sine squared t, all into the square root. Well, that's 1, so this is 2 over root 5. All right, okay, now we're almost done here. So let's see here. Our formula for curvature said this. It said curvature is 1 over the length of v times the length of t prime. Right, okay, so we got all this stuff now. So it's 1 over root 5 times 2 over root 5, which is 2/5. All right. Okay, so what does this tell us? Well, there's constant curvature to this helix. Why would that be true? Well, so constant curvature at every point. Well, think about it. A helix in the xy plane has circular cross sections, right? So you're constantly turning at the same amount every time. You're moving in a circular pattern. So you're turning always at the same rate to move around the circle, right? Okay, there's never any point that's got more or less turn in it than another point has. So this makes sense since helix is a circle in the xy plane. Again, there's never any point where you're turning more or less than any other point. It's a circle, right? Okay. Well, let's see what n looks like. Let's see, where do I want to put n? Let's put n over here. So there's n. What was n? N was just, what, t prime of t over the length of t prime of t. Is that what I have back here? Where am I here? Yeah, that looks good. So t prime over its length. This is going to be a unit vector because it's going to have length 1. So t prime is this junk over its length. Let's see. So we're going to have, let's see, that will cancel. That will cancel. We're going to wind up with negative cosine ti plus negative sine tj, right? This is going to cancel itself out. And what I've got, it is good, yeah. And so think about this. Remember, n is always pointing in the direction that the curve is turning. Well, this is a circle in the xy plane, so n is following a circular pattern around, right? So unit normal vector, well, it rotates in a circle in the xy plane. And what does that show? It shows the direction the curve is turning, right? So imagine n is rotating constantly in a circle around itself, right? And as you're doing that, the helix is doing the same thing. It's coming around in a circle as well. Okay, so none of these were surprises here with the helix. All right, and that concludes the section on curvature and unit normal vector n.